x. F of x is x plus 1 over x. The interval is 1/2, 2. Verify the hypothesis of Rolle's theorem and find the guaranteed C. So number 1, verify that Rolle's theorem is applicable. And in number 2, find C, guaranteed by the Rolle's theorem. Okay. So first of all, I have three hypotheses to verify. One of them I have to explain why this function is continuous, if it is continuous on the given interval. So number 1, f of x continuous on 1/2, 2. So this is continuous everywhere, and this is not continuous at 0, but 0 is not here. So as a sum of two continuous functions, the function is continuous on 1/2, 2. Number 2, f of x differentiable on at least open interval 1/2, 2. There are no problems. This is differentiable everywhere. We know the graph of this. Here's the graph of 1 over x. Between 1/2 and 2, differentiable, no corners, no nothing, no cusps, differentiable. As a sum of two differentiable functions is differentiable. Now, number 3, I don't know. I have to find f of 1/2, and I have to find f of 2. So Rolle's theorem says these have to be the same. Otherwise, you cannot apply it. So I don't know. We'll see. So here's the function. 1/2 plus 1 over 1/2, I get 2. And the other one, 2, plus 1/2. I don't even need to calculate anything. Are they the same?
Yes.
Thank you. So all three conditions are fulfilled. So therefore, there exists a C, at least one, in the open interval 1/2, 2, such that f prime of C is 0. So I'm going to copy the function here, x plus 1 over x. So can anyone give us the derivative of x plus 1 over x? The derivative of 1 over x has to be memorized. It's very important. Sorry. I thought somebody wanted to say something. Sorry.
1 plus
Careful.
1 over 2 times the square root of x.
Careful.
I'm sorry.
So let's do this one more time because this is very important. So 1 over x is the same with x to negative 1. When we differentiate x to negative 1, we get negative 1 times x to negative 2. So this is negative 1 over x squared. So please frame it somewhere. 1 over x prime equals negative 1 over x squared, because I need this in chapter 5 when we go backwards. So 1 over x prime is negative 1 over x squared. If you forget, just do this a couple of times so you don't forget. So of course I have x squared minus 1 over x squared. And now I have to set it equal to 0. When is a fraction 0?
When the denominator is 0.
When the numerator is 0. And of course we know we have to get two solutions, and we know how. Okay. So remember our interval is 1/2, 2. Which one do I have to choose?
+1.
That's it. Okay, so this is guaranteed by Rolle's theorem. So C is 1 by Rolle's theorem. And there are other applications based on Rolle's theorem. I just would like you to at least be able to find the C. If we have time, we can go to other more sophisticated applications that involve Rolle's theorem. But for now, I'm happy with just finding C. Any questions? You think we need another example with finding C, or is it clear? It's just the critical number, basically, in that given interval. It's nothing else. Are we okay? Say it again, Dixon. I couldn't hear you.
Yeah, so my question is, how are we able to check off the fact that f of x is continuous?
Oh, because we talked on the continuity, we said that any combination, addition, subtraction, multiplication, division, even function composition of continuous functions is continuous as well. So if I give you two continuous functions and you add them, you get a new continuous functions. If you subtract them, multiply, divide, or function composition, you will also get a continuous function. Was that the question?
Oh, that's it. That's okay.
No, did you have something else and I didn't hear your answer or your question?
Oh, that's fine. I just wanted to know how why we checked it off as being continuous.
We have to check. We have to check that it's continuous. We have to check that it's differentiable. So in this case, we had x plus 1 over x. This is continuous everywhere and differentiable everywhere, and this is continuous everywhere and differentiable everywhere on 1/2 2. Guaranteed. Because of the graph. And polynomials are always continuous and differentiable. Is that okay?
Yeah, that's fine.
Okay. So one other theorem we need to talk about is the mean value theorem. Okay, so let's look at another function this time. Point A, point B, of course, our best friend A comma B, of course, f of A, of course, f of B. Of course, I draw the line segment A comma B, AB, I meant to say, not A comma B. Okay, and now let's follow. I used to have a little ruler here handy, but I don't. So, okay, so this is a calendar. So follow me for a second. Okay, so this is the line AB, and I am going to draw a parallel line tangent to the graph. So this is tangent here, and this is the line segment connecting A to B, and they have the same slope. So slope of this and slope of this are the same because they are parallel. So first hypothesis and the second hypothesis are the same hypothesis from Rolle's theorem. F of x continuous on the interval a comma b, and f of x differentiable at least on the interval. We don't care what happens at endpoints. Continuous, differentiable, no cusp, no corner, no vertical tangent, and that's it. The Rolle's theorem, mean value theorem, also known as MVT, has only two hypotheses. Then, by MVT, there exists, of course, a C, of course, in the open interval a comma b, such as, or such that. And now let's discover. Can anyone give us the slope of the line AB? We're only looking at the line AB. Can anyone discover for us or tell us what to write for the slope of AB?
F of B minus F of A
Excellent.
over B minus A.
Excellent. Perfect. And now forget about that. Can anyone give us the slope of the tangent line to the graph at point? I don't want to use, I'm going to use D. Can anyone give us the slope at D?
Also f of b minus f of a over b minus a.
Correct. In a different way. Excellent. But I need it in a different way. Is there another way of representing the slope of this line? Tangent to the graph of f of x at D.
Prime of B?
Very good. Absolutely. So the rate of change at this point, because this is a tangent, the rate of change, f prime at C, is the slope of the line at D. So we already noticed that these two have to be the same. And that's it. That's the mean value theorem, such that f prime of C equals f of B minus f of A over B minus A. This is MVT. Let's see how we apply this. Yes, let's look at a natural log. Okay, here's an example. We have f of x equals natural log x, and the interval is given to us as 1, 4. They're asking us, number one, is MVT applicable? And number two, find C. Find C guaranteed by MVT. Okay. So there are two hypotheses. Number one, f of x continuous on 1, 4. Would you agree? So remember the graph of natural log. That's why we need to remember these graphs. So we don't have to graph them all the time. And 1 is here, and 4 is somewhere here. Is this function continuous on 1, 4?
Yes.
Is this function differentiable on 1, 4? At least the open interval 1, 4?
Yes.
Good. So then by by MVT. There exists C in the open interval 1, 4, such that what? What do I have to write?
F prime C equals
F of 4.
F of 1. Oh yeah, F of 4 minus F of 1
4
over 4 minus 1.
4 minus 1. That's it. Okay, F of 4. So I'm not going to write here because this is an equation. Okay, so F prime of C, it's very clear, 1 over C, because that's natural log. F of X is natural log. So F prime will be 1 over X or 1 over C equals F of 4, natural log 4. F of 1 I know is 0. 4 minus 1 I know is 3. I flip both. So C equals 3 over natural log 4. And you can say, wait a minute, is this in 1, 4? Okay, we have to check to make sure. So 3 divided by natural log 4. And if this number is not between 1 and 4, then we either have an error and we have to redo the problem, or something else is wrong. As expected, 2.16. So approximately 2.164. It is indeed in the interval 1, 4, and it's guaranteed by MVT. Any questions?
Where did we get the 1 over C L 4 over 3?
So the derivative of the function is 1 over x, but I need 1 over c. So f prime of c is 1 over c.
Okay. I get it.
Better?
Yes.
Okay, so can we upload just this last problem so we still have a few minutes to continue? So let's take one